So this is chemical reactions and energy for year 11, lesson 2. We're going to look at making and breaking bonds between pages 9 and 17, and hopefully you've numbered your booklet from lesson 1. So when a chemical reaction occurs, the reactants are changed into the product. So what you start with are called the reactants, what you end up with are called the products. Now this diagram down the bottom here just shows you that when you make bonds, energy is given out, and when you break bonds, energy is taken in. That is something you're just going to have to know. So try and fill in the blanks from your booklet. Now when a chemical reaction occurs, the particles or the atoms or molecules have to have enough energy to become the products. So enough energy has to be supplied to them to overcome something called the activation energy, and all chemical reactions have to undergo an activation energy. It's the minimum amount of energy needed to start the reaction. Think about a high jumper or the frog jumping over those high barrier of rocks and then a lower barrier of rocks. So some reactions will occur more quickly because they have a lower barrier, they have a lower activation energy, so they occur more quickly and more easily. So if you're looking at this energy level diagram, energy is going up here, and that's the progress of the reaction. So the reactants are what we start with. There's particles there. They have to overcome this hump here. They have to get enough energy to overcome the activation energy before they can become the products. So bonds have to break in the reactants, and then they're remade to make the products. This will become clearer as we go on, I'm hoping. So this is an energy level diagram. What you need to label is the overall energy change, and you can see all that is the height difference between the reactants and the products. So it's that length there. It's the height difference between the energy of the reactants and the energy of the products. That's the overall energy change. And that will tell us whether something is an exothermic reaction or an endothermic reaction. Okay, so that's in your book. You need to label that. So the overall energy change. So telling you whether something is an exothermic or an endothermic reaction. Now we know, if you read the lilac colour or the purple colour, energy is taken in to break chemical bonds. And we know that energy is given out when bonds are made. You have to just know that. The overall energy change is the difference between the energy taken in to break the bonds and the energy given out to make the bonds. Now some of you might like this, and it might help you remember. Breaking bonds is endothermic and making bonds is exothermic. So endothermic energy is taken in, exothermic energy is given out. You've got this in your book, and you can fill it in from the previous slide. Now you've also got this page in your book, and you will need this slide to complete it. Now this slide shows you the energy level diagram or energy profile. You have to know those. Now there is a difference. The reactants are higher than the products in an exothermic reaction. The reactants are lower than the products in an endothermic reaction. But they've still got, look, the activation energy. At 1, you've got the overall energy change is exothermic, the arrow's going down, and in here the overall energy change, the arrow's going up, it's positive. So these graphs are drawn into your book, please. What I'd like you to do then is to look at the previous graphs and try and work out the blanks. Now I've given you less or more here. I want you to choose which one is correct for each one, and then the blanks you fill in. So then you've got this, write down 2 exothermic reactions which can be used to provide heat at home. Think about anything you can burn at home. Then you've got an energy level diagram, and you've got some questions there. Do your best. Now catalysts are chemicals that will speed up a reaction. And they do this by providing a different route with a lower activation energy. Now you can see this is the normal route that the reactant takes, and you can see it's got a big hump for the activation energy. But when you add a catalyst, which is just a chemical that will speed up the reaction, the reactants take a different route block that has a lower activation energy. Okay, so that's why the catalyst speeds it up. So what they do is they provide a different route with a lower activation energy, and you're asked to show this on the diagram, and all you need to do is to draw a small hump block. I just put one in here. It doesn't matter where you've put it as long as it's lower than the original. And that's your activation energy height this time. Right, it's a much smaller arrow, and that shows you a different route with a lower activation energy using the catalyst. So the blue curve there is a different route with a lower activation energy when I add a catalyst to the chemicals.